Hi guys, before we get started with the tutorial, I just wanted to let you all know that all these mechanics that we're going to set up today, you can test out in this little kind of firing range I've set up. So if you want to test out how these different approaches work before you set them up yourself, this is going to be up on itch.io. There's a link in the description and also a link to a video that explains this fire range setup in a bit more detail. That being said, let's get to the tutorial. Hi everybody, Vigorous Rapscallion here with another VR design tutorial. This is going to be part 2 of our throwing mechanics tutorial, how to improve those throwing mechanics. Now, you might remember in the last video, I said there were a couple of ways to solve this problem of getting different behavior from the thrown object depending on where you throw it or pick it up in your hand with. Now, I like the snap solution. That's my preferred way to do this, but in case you want to see another way, and we'll see how this is more relevant to kind of bigger objects as the tutorial goes on, we're going to look at another way to solve that issue and get a consistent feel from the throw every time. And we're going to do that mathematically. What we're going to do is we're going to get the distance between the center of mass of the object and the center of mass of the hand, and we're going to get the cross product of that. So that's going to give us a vector moving forwards that's sort of in between the two. And that way it's the same no matter where you picked it up from in the hand. It's going to feel the same when you throw it. So let's see how to set that up. Alrighty, so here we are in our blueprint for the throwable 3 pickup object. As I mentioned last time, we were going to steal some code from that pistol setup. So this is all we're really going to take from it. All this does here, it tells us what hand picked up the grab component. So it's going to give us a boolean. In the case that it is the right hand, this will output to true. In the case that it is false, it will output to false. So to get a reference to the correct hand, first we're going to need a reference to our VR pawn. So let's get an actor of class, and we're going to grab VR pawn here. Great. Then we are going to go ahead and get a different return value from this depending on if it is the right or left hand. If it's the right hand, we want the grab component from the right hand. If it's the left, the grab component from the left. So it seems like the thing to do here is to grab a branch. And then, in the case it's the right hand, we want a reference to the right motion controller. So let's search up motion controllers. Probably going to be way at the bottom here. And let's get the right grip. Then for the other case, we're going to want to get left grip. There we go. Then for both of these cases, we're going to need a reference to where the object is when it's picked up. So let's go ahead and get location. There we go. And we're going to do the same thing for both of these. Get world location. And get world location. Now we're looking for the difference between these two locations in space. So we're going to need another variable to keep track of those. Let's call that pickup offset. And we're going to need that to be a vector. And in the case that we have the right hand going here, we are going to do this minus the location of the hand. And in the case that it is left, we're going to do the same thing, but with the left grip location. So subtract as well. And there we go. Now we've got our pickup offset set, depending on what hand it was picked up with. Next, we want to get the cross product between the angular velocity and that distance we just got there. So let's go ahead and get the same average that we've been using. Do cross product. Grab our pickup offset, plug that in, and then add these two together. I meant add. Alright, there we go. Alright, let's check it out. Okay, let's take a look at these new modified ones and see how they differ. Once again, I know it's kind of hard to see on video, so just as a heads up at the beginning of the video, I am going to be releasing a little program on itch so that you can try all this out yourself. That's going to have the different ways of setting up the objects labeled, so you can throw and get a feel for how the different ones feel before you decide which one you're going to set up, if you prefer to do it that way. But let's take a look. And then let's grab down there.
Wow! Wow!
And once again, I know it's hard to see on the video, but you are getting a way more consistent feel out of this, whether you pick the object up from the middle of your hand or the end of your hand. Throwing it feels exactly the same way each time, which is pretty neat. The only reason I'm not a huge fan of this solution is that it kind of normalizes things towards slower, which just isn't as much fun, in my opinion. But there's ways to fix that if you do like this solution, and we're going to look at how much bigger of a difference it can make when you've got an object that is not perfectly round or where the center of mass is above or below or outside of the hand in some way. So let's take a look at that next. Okay, so let's take a look at how things start to get more complicated once you're no longer dealing with an object that's perfectly round or where the center of gravity is within the player's hand. So let's do a sword. Swords are not famous for being fun to throw, but that's what we're going to start out with anyways, and show you kind of a couple of the foibles you're going to run into. So first, let's grab a sword. I just whipped this up in Blender really quickly. It is not a good sword. It is like the sword that Viggo Mortensen pretends is good in Lord of the Rings. But it is a sword, and it's not pretty, but it will demonstrate what we need it to demonstrate. You can't really see it here, so I'm going to go ahead and add another static mesh. And let's call this sword a demo. And we're going to switch that to another instance of the sword mesh. Now, what's interesting here about the way that Unreal tracks velocity is that it does not do it from the center of mass, which we're going to go over what center of mass is and how to find it on your model in just a moment. But this does not take the center of mass as the sort of point that it's checking velocity at. It takes this origin point, which is set when you import the static mesh originally, or if you're downloading assets, it's already going to be on there. And it's kind of a pain to change, to be honest. Once you've imported the object, there's no permanent way to do it in Editor. You can do it per object, but that's not a great solution. And of course, if you're getting assets from somewhere else, you have to export them into whatever your 3D solution is and change it that way. Which can be a little bit of a pain too. But before we talk about how to change that or a couple of workarounds, let's go ahead and see what kind of behavior you get if you try and use the sword just as is, with its pivot point really erratic way up there at the tip of the sword. Okie dokie, so let's take a look at the swords. Now remember, before we throw this thing, that where the velocity is being stored from is right here up on the tip of the sword. So obviously that's going to be going way faster than your hand and have way more angular velocity when you release. Let's see what that looks like. And you can see it just goes over the horizon. Let's try that again. Let's try an underhand throw. Oh, look at that. And beyond that, when you release, which once again is a little hard to see in the video, it tends to go from way higher than where you released from. And that's back to that issue of getting the cross product between the center of gravity of the object and the hand. So that's feeling weird. So there's a couple things we could do here, but the first thing I want to do is go ahead and implement that cross product and see if that makes at least the direction of the throw feel okay, and then we'll deal with that velocity issue. Let's take a look. So in order to apply that same cross product function to this object, you could either copy paste everything we did in the previous step, or probably easier is to duplicate that object and just change the mesh. Do whichever way appeals to you more, but figured it'd be a waste of time to go over the whole thing again, and let's take a look at how it behaves differently. Alright, so we've got our old sword set up in red here, the new one set up textured. Let's take another look at those. And yeah, because the velocity is being gathered from so high, we are getting that super strange behavior. Let's take a look at these with the cross product, where it's still getting the velocity from that same point. And you can see that changes things quite a bit, but they're still not really going where I'd expect them to. And that's because, I'll use one of these as the example, the cross product we're getting is not from the center of mass, it's from way up here, and that's creating a vector kind of in the middle here, whereas we more want it kind of between these two. So how are we going to change that? Like I said, we could change it in model, but we're going to show how to do it in code real quick. So to change how we're getting that cross product, we're just going to grab this get world location and instead get the center of mass. There we go. Plug that in, and let's see if that feels different. So, same deal, old ones in red, new ones in texture. Take a look at those again. Still feeling pretty weird. Those are feeling way better. It's still a little inaccurate. It's definitely pulling high. And part of the reason that it's kind of kicking off is even though we've changed the vector it's coming out of, since it's still getting that velocity from up there, if you twist the sword, you're going to end up with a much higher Z velocity than you intended to. So it's going to end up going a lot further up than you meant it to. So without changing the model, let's also change where we're gathering velocity from and try that. So to do this in code, luckily it's pretty easy to do because Unreal has a great function built in for this. Let's grab our object and get linear velocity again, except you'll notice this. Get linear velocity at point. Now, the point in question is going to be a point in world space. So you can't just type in an offset here. That's not how it's going to work with this particular function. So to make sure that this is the center of mass of your object, once again, we're just going to get center of mass and plug that into the point. And now, without having to change the model at all or change how the location works, that's where the velocity is kind of going to be referenced from. Now, you might be wondering, isn't that an issue up here when we set linear velocity? Because that is setting it not at a point, but at the default point. And just in case you're wondering, no, there is not a set linear velocity at point. Why is that? Well, because it doesn't really matter. That's going to be the velocity of the entire mesh, and it's not the angular velocity. So the angular velocity is already going to be applied to wherever the center of mass is. That's all well and good. Whereas this is just going to be kind of the entire model. So it doesn't matter if the tip of the model is moving at a certain vector or the base of the model is moving at a certain vector. The whole model is going to move at the same vector no matter where you apply that force. Okie dokie. So we got our newest swords here, the ones that are gathering velocity from the center of mass there. That's actually more like there, which is probably still a little high. So the functionality we're getting is a little weird, and we could definitely go back and modify that. But they do seem to be flying forwards, more or less in a way you'd expect from the way you throw them. They're obviously not very useful as like a weapon. It'd be pretty hard to hit something with that, but that's not too out of the ordinary. I don't know if you've ever tried to throw a sword. It doesn't come up much. It's very difficult, unless you're Russell Crowe in Gladiator, who seems to be able to just chuck that thing like 40 feet and just hit right on the money. I love that movie. Anyways, that doesn't happen in real life. So in part 3, we'll come back to the sword and sort of do more stylized things that would make it more of a viable throwing weapon, as well as doing some throwing knives, ninja stars, fun stuff like that, that doesn't tend to work quite that well in real life. But for the rest of the realism throwing video, let's go back to our snap ball for a moment, because this solution doesn't rely on that cross product, which is great, except it doesn't really feel that good.
No!
Since the realistic position for the ball to be in is way down here in the center of the hand, you're having to put a lot more momentum into it, and it's not really getting that feel like when you throw a real baseball, where you kind of let it roll off your fingertips at the end.
No!
So it's just not that great to throw. And we could just, as we did in the last video, just pump up the lateral values for its velocity. And that's one solution, but it'd be better if we had something that felt like it relied a little bit more on player input. So let's see how we... Okie dokie, so as usual, we're going to start with the duplicate. We're going to call this baseball spin to velocity. Okay, so what we're going to be trying to do here is take this angular velocity and create some kind of scale value to add it to linear velocity. So what kind of values are we dealing with? What we've got down here is the angular velocity in radians. So let's just use some prints to get a better idea of what we're looking at. I'm going to look at each value separately. There we go. And all this good stuff down here, I just added in a little function to reset where the object is after you throw it. It's not really necessary to the tutorial, so don't worry about that too much. But what we are going to worry about is printing all 3 of these out after all that happens. So we're going to need 3 prints. And then we're going to grab all this info. Which is pretty messy, but this is just going to be temporary. And let's try a couple different things and see what kind of information we get. Okay, so one little tip when you're doing kind of debugging logs like this, in order to make things easier for yourself, using different objects is a great option because the log is going to tell you what object it's in reference to. So let's pick up one ball and use this ball to try throwing with no angular velocity. Just as much up and down as we can. Great. So 3 should do it. Then let's do one where we try and flick our wrist this way. Let that come back. And then let's do one where we flick our wrist backwards. And then let's see what type of information we're getting. Okay, so let's take a look at our outputs here. I probably should have added labels to these with an append, but no worries, we could figure it out. They're going to be in batches of 3. So you can see this one where I tried my best to have no angular velocity. Then you see this one where I was spinning forwards. And then this one where I was, oh no wait, it's this one where I was spinning backwards. You can see the main thing that's changed is one of those planes is negative. And now, because the way that we're measuring rotation, that can really mess things up. And if we're trying to make a scalar value, then we probably want all these to be an absolute value. And since we're just trying to get the overall velocity, we probably want to add them all together too. So let's try that, test again, and see what kind of information we get. So first we're going to come back and disconnect these from the print. We're going to go ahead and get an absolute value for each one. It's ABS. And that's just going to, if it's negative, it's just going to give us the positive version of that negative number. Let's grab 2 more of those, hook that up. It'd be great if I clicked on the right thing. Boom. Boom. And we're going to add them all together. And just go ahead and add another pin on here. Oh, I think you got to be disconnected for that. You do. Add these three together. And then we're only going to need one of these prints over here. And just for neatness sake, we got to get rid of all these little converters that pop up in random spots. Delete, delete, delete. No, that's for later. And then grab these and bring them on over. So let's see what kind of total values we're getting and what we could do with that. Okay, so I've gone back in and done the same type of testing where I tried 3 with each one. And let's look at what type of values we're getting. So when we're really not trying to have angular velocity, there's still going to be some. Looks like about 16 for the highest one. When we're really trying, we're getting between, for just one vector, we're getting between like 37, 44. Same deal when I tried to do it backwards. And this one was kind of a sidearm throw where I tried to put multiple different directions of spin on the ball. And you can see that comes out considerably higher. That's kind of fun because since we're tracking from a few positions, kind of the more intense your movement is, the more that's going to bump things up. So let's just call our maximum that we're hoping for 60. And how much faster do we want the ball to go at that level? Let's say 2 times at the highest level there. So how are we going to accomplish that? So obviously if we want 60 to give us a value of 2, well that's pretty easy. We just divide by 30. So let's try that. And while we're at it, let's just go ahead and promote this to a variable. And we're going to call that... Nope, I didn't mean for a new one. Meant to rename that one. There we go. Let's just call this... spin multiplier. Great. Now there is still one problem with this that I don't really like, and let's go back and take a look at that info again. So say you didn't really put any pepper on the ball at all. Well, for instance, like this one, 6 divided by 30, you're going to get, you know, what, 0.2. So that means the ball's like barely going to go at all. And you don't really want that either. You don't want, you know, it to feel really punishing. I feel like there should kind of be a cutoff. So let's just make the cutoff 1. Anything that's going to result in under a 1 times multiplier will be ignored. So to make sure that this isn't factored in when it's below 1, we could do a couple of things. We could kind of normalize the value, or we could use a branch, because the other option is going to sort of squish this value, so it's also going to have a lower cap. So let's use a branch instead. And if this value is less than 1, then we just want to do what we've been doing. We just want to set the physics linear velocity off of that array average. Now in the case it isn't, we're going to need another one of these, and how are we going to deal with this information? So we could, like we did in the last video, split this struct pin and only apply this to lateral movement again. But I don't think that's really necessary here, just because of, you know, kind of how we're measuring the spin and everything. It doesn't feel that unnatural. It doesn't really feel like the ball popped out of your hand. So what we can do instead is just to straight up multiply. But we're going to want to do that by a float. And we're going to grab that same info from way back here. Sorry, I know this blueprint has gotten pretty messy throughout the tutorial. I will clean this all up before part 3, because it's going to get even more complicated. Alright, so that is multiplying by our scalar value on the in the case that that value is over 1. If it's less than 1, it's just going to go by the default. And then we got to hook that up back to the rest of this chain. Let's see how that feels. Oh, and I had forgotten to hook our object up as target when I copied physics linear velocity there, so there's that. Okay, so let's take a look at these modified to take in the velocity too.
Wow!
Those feel a little better, but what I really like about it is you can kind of learn how to throw this ball differently and get different functionality. Just like with a real baseball, you probably aren't going to do a kind of hammer throw like that, and this will work better if you don't. If you do more of a throw with more motion on your wrist, you're going to get more velocity out of the ball. And then it's also not too punishing if you put no angular velocity on it. It still flies, not very well, but it doesn't just pop down to the ground as it would if it was multiplying that value by 0.2. Oh my goodness. And yeah, it feels good. It feels like something the player can get better at, can get used to, and find different ways to throw more quickly. So, yeah, I really like the way that works, but if you still wanted to pump it up a little bit more, you could do the same general multiplying of the lateral value, or all values that we did in part 1, to make it fly just generally faster as well. Okay, so we got a bunch of javelins in front of us, and these we have gone all the way back to the end of part 1, the throwing mechanic we had set up at that point. And the reason for that is we're not going to need a lot of that stuff. So the javelin here, the pickup point, the center of gravity, and the center of the object are all at the same place, which is where I have it picked up right now. And that feels terrible. That's largely because if you try and throw a javelin in the way that you would in real life, which is to kind of roll over your shoulder and let it come out of your palm, that's not going to work right here. And it's not going to gather a lot of velocity. Beyond that, as I said, things just spin a lot more in Unreal than they do generally. So let's do two things. One, let's just generally pump up the velocity on release of this thing, and let's just get rid of the spin entirely for now and set it ourselves later. So how do we want to set this up? For the feel of this, what I was going for was maintaining realism while still making the player feel like they are really good at throwing a javelin. But just in like a normal athletic person kind of way, not in a like rocket-powered javelin type of way. And I messed around with this for a bit and didn't want to put it all in the video, so here's the values I found work pretty well. We're going to multiply all of these, let's duplicate those. Great, and I personally found it feels good for Z to get a little bit more of a kick than the others. And that's because, once again, of the way you throw a javelin, it's going to be kind of hard to impart a lot of velocity on the Z-axis. So we're just going to pump it up even more. And sorry for the obvious cut here, but I did forget that you're also going to want to take out the angular velocity entirely. You don't want to get rid of this because you're going to want it to set itself to 0, 0, 0, at least for now. Okay, I've modified the javelins a little bit. I did also change the grab component, which I'll probably go back and change a little more too. It's just something you got to adjust till it looks right and feels right in the hand. But still as is, let's see how these look. And that's fun. They fly really far. If you do it more just laterally, they still feel like they're jamming on that plane, or you can get real crazy with it. And there you go. But as you can see, major problem is that whatever rotation you release it at, that's the rotation it's going to keep. So it looks good when the player's playing nice and, actually throws it like a javelin. Let's say you just go like that, and now it's at a really funny angle. So how are we going to get it to kind of look like a javelin moving through the air in that parabolic arc where it's sort of pointed upwards as the Z velocity is positive and downwards as it's not? Well, there's your clue right there. How do we create some sort of relationship between that velocity and the direction of the javelin? Let's do that next. So first of all, whatever function we're going to end up writing here, well, we don't want it to be happening all the time. Then the object is going to be doing weird things while it's just sitting. We really only want it to do this when it is thrown. And if we were really setting this up for a game, we would also want this functionality to stop once the object hits something. But we're not going to worry about that for now. It's going to be complicated enough. So first thing we're going to want is a variable to tell us if it's been thrown. So let's just call that is thrown. And as soon as it's dropped, one we want is thrown to be false by default, obviously. And then we want to set is thrown to true. And simple as that. Then we can just plug that into our existing logic. And what are we going to do with it? Well, luckily, once is held is false, we're going to be executing the other branch here. So we're going to go ahead and grab that. Bring this nice and far down so we got plenty of room. And we're going to grab our is thrown, and that's what we're checking again. In the case it's true, once again, we want to take the z velocity and create a relationship between that and the rotation. So first, let's take a look at what that z velocity looks like so we can get an idea of the type of numbers we're working with. And to do that, we're going to go ahead and grab the object and once again get linear velocity. And this should work fine because the center of gravity is the same as the center of the location for this object. So we shouldn't have to do any work here, which is one of the advantages of setting it up in the first place so that those two things match up. But let's go ahead and print out our z value. And we are just going to let it print once a tick. It's going to be a lot of info, but it'll give us some good fidelity for what we're looking at. So let's see what we can see. And just so that we're not getting this information forever after we throw a javelin, let's set this delay to 3 seconds, and once that happens, let's go ahead and set is thrown back to false. Alright, let's try it out. Okay, so these will start logging their velocity on the z-axis when we throw them. Let's try a couple just on the lateral plane. We are still getting some strange behavior on rotation. We'll take another look at that. There we go. And then let's try throwing one as high as we can. There we go. So we can get an idea of kind of what that peak V or Z velocity is. And let's just throw one off the side from here. And that should be enough info. Let's take a look at what we got. So after looking through all of this information, which there's a ton of, I found that it seems like the cap from the player releasing the Javelin is about positive 800. And now terminal velocity in Unreal, you can see I got one a little higher than that, around almost up to 1500. And terminal velocity in Unreal is, I believe, 4000. So it will get there eventually, but that's really not going to come up in our gameplay at all. You know, for the most part, we're going to be throwing on a lateral plane, and we don't want this to be pointing like straight up at the beginning and straight down at the end. We kind of want it to, you know, feel a little bit more balanced. So let's try a couple of values and see what ends up feeling good. So let's go ahead and move this print string. Actually, let's just get rid of it for now. We might bring it back later. But what we're going to want to do next is to set the rotation of the object. Not the angular velocity, but just the rotation itself. And we're going to be doing this once per tick. We're going to want to do set world rotation. Then we're going to split this pin here. And what's the relationship we want? Well, up and down in Unreal is going to be Y here, the pitch. But we want that to be related to the velocity up and down, which is going to be Z. So we're going to plug Z into Y. But we already know that's not really going to work because this Z value is going to be much, much, much higher. And what it's going to end up doing is just spinning around. So that's not going to work well. But we're going to leave it plugged in like that for now. And then what do we want for X and Z? Well, we want them to just stay the same as they were at the point of release. So, since this is going to start executing as soon as the Javelin leaves your hand, we can go ahead and just get rotation, world again, split that struck pin, and we're going to plug our X into our X and our Z into a Z, and we're not going to do anything with this. Now, just because the video is getting a bit long, I could go over how I arrived at this number, but I found a good number to scale this is by dividing it by 20. Since it doesn't really seem to get above 2,000, even though the terminal velocity is potentially a lot higher, that's going to be just a good option. That's going to make it look nice. So let's do divide. And what we actually want to do here is negative 20, because as it stands, this is going to create the opposite relation we want. The higher the Z value, the more the object is going to point down and vice versa. So we want to reverse that, and all you do is make that a negative for your divisor instead. And now it's going to be pointing up as it goes up and down as it goes down. Okie dokie, let's see how they work now. Let's just do a gentle toss so it doesn't go too far out of sight. And look at that. You can see how it arcs downward as it starts moving downwards. And you can sort of tell there's a little behind the scenes work going on here. But for the most part, it flies really well. It makes you feel like you could actually throw a javelin, even though if you're like me, you definitely can't. But it's a fun mechanic. So that's going to be all for today's video. Like I said, in part 3, we're going to get into some really stylized stuff that really does not work like the way that stuff in the real world does, but will feel like a lot of fun for the player. Before we get to that, though, there's a couple of things that are going to be relevant to that part 3. So for the next couple weeks, I'll be doing some tutorials on improving your pickup so you don't have to, actually get over to the object. There we go. So you can grab it at a distance. And I'm going to be going over aim assist in VR, which works a little bit differently than it does in first person. It's a similar concept, but believe it or not, those concepts are going to be related, and then both of those concepts are going to go into how we make these throwable objects even more fun. Before I get to that, even though, next week is going to be a little fun break. Every couple of videos, I'm going to do a fun mechanic that probably isn't a good idea to put in your game, but that will teach you a lot, sort of in the sense that you often learn more from mistakes than you do from doing things correctly. So I hope you'll tune in for that, and remember, if you want to try all this out, it's up on itch.io. There is a link in the description, and that's just going to be a kind of range setup where you can try out throwing these different objects and adjust their settings. So I hope you'll give that a look, and I hope you'll tune in next week. As always, thanks for watching. Have a great day.